Welcome to Summarize Science. Testing self-driving cars in the real world is expensive, time-consuming, and potentially very dangerous. To get around this, developers often use offline evaluation, where they test their AI models on pre-recorded driving data. The problem is, a model that looks good in these offline tests can still perform badly and even crash when put into a real car. This paper investigates this critical disconnect between simulated performance and real-world safety. The researchers' first step was to confirm how bad this disconnect really is. They found that in complex, realistic driving scenarios, the correlation between standard offline tests and actual online performance was even worse than previous studies had reported. This casts serious doubt on the way many driving policies are currently evaluated. So, they came up with a new hypothesis. The most important errors are the ones a model makes when it's uncertain. Think of it like a human driver in a confusing, new situation. That's when you're most likely to make a mistake. The researchers believe the same is true for an AI. They created a new metric called uncertainty-weighted error, or UWE, which specifically focuses on and heavily penalizes errors made during these moments of AI uncertainty. These graphs show the results from their extensive simulations, and this is where it gets really interesting. Each dot is a different AI driving model. The vertical axis represents the actual online driving score, where higher is better. For the old metrics like QC and TRE, you can see the dots are scattered all over the place, showing there's almost no relationship with the real-world score. This means they are very poor at predicting which AI models are actually safe. Now, look at the top left graph for the new UWE metric proposed by the authors. The dots are much more tightly packed along a clear trend line. This demonstrates a significantly stronger correlation, meaning this new metric is far better at predicting a model's real-world driving ability just from offline data. In fact, it showed a 13% improvement in correlation compared to the next best metric. To make sure these results weren't just a quirk of the simulation, the team went a step further. They built and tested their models on this small-scale, real-world robotic car. It's equipped with a powerful computer and a camera, allowing them to test the AI models in physical environments with real turns, obstacles, and lighting conditions. The results from the physical robot backed up the simulation findings perfectly. These charts show how well each offline metric correlates with different aspects of real-world driving. The blue shape, representing their new uncertainty-weighted metric, consistently covers the largest area. This shows it was the best predictor of everything from overall success to specific events like collisions and traffic infractions. So let's recap the key points. Standard methods for testing self-driving AI offline are poor predictors of real-world safety. The researchers discovered that the key is to focus on the AI's uncertainty. By creating a new metric that heavily penalizes errors made when the AI is uncertain, they could much more accurately predict how the model would perform in a real car. This groundbreaking result was validated in both complex simulations and on a physical robot. What could this mean for the future of autonomous driving? This work is a major step toward making the development of self-driving cars safer, faster, and more efficient. Instead of relying so heavily on risky and expensive on-road tests, developers can now get a much clearer picture of a model's safety from offline data. This simple but brilliant idea could help accelerate the arrival of truly safe and reliable autonomous vehicles on our roads. Thanks for watching Summarize Science.